The 3D models and the color charts were put side by side. First, the cold dark matter universe, and then the Iris Galaxy universe. Whatever way you looked at them, they didn't fit.
These new results leave us with three choices. We can make some adjustment to the cold dark matter model, which is so successful in many ways. We can introduce some new ingredient into the model. For example, a trace of hot dark matter would help to give structure on large scales. Or thirdly, and this is the most interesting possibility, we can look for some completely new theory of how galaxies form.
As the microwave background anisotropy measurements get more and more precise, what we find is we don't find any fluctuations. And that means that the cold dark matter theory is in real serious trouble. And if we don't find something very soon, we'll have to abandon that theory. And though I want very much to find the fluctuations, if I were a theorist, I'd be getting a new model ready.
It seems to me clearly premature to throw away a theory which is so successful in many ways. It seems to me the reasonable attitude to take is to go back to the theory and try to modify those aspects that appear to be particularly weak. But ultimately, there is an obvious proof or disproof of a theory which is based on the predicate that exotic particles should exist. And that is, let us go and look for the particles. And if we find them, then we clearly can claim a great success. If we don't, then at that point we ought to throw the theory away.
But where do you find cold dark matter? Professor Peter Smith and his colleagues began the search.
It was quite easy, in principle, to detect these particles. What we preferred was the idea of a very heavy particle, and there are a number of ways of observing this. And the way you can see it is if that particle hits an atom, that atom will in fact recoil. Now we have a number of ways in which we can see these recoils of the atom. First of all, the recoiling nucleus has enough energy to produce free electric charge in the material. And that electric charge can be collected, measured, and that tells us about the energy of the recoiling nucleus. The second way is rather different. It collides with the atoms in the material, gives them energy, and that is effectively heat. And that heat causes a rise in temperature of the material. Now this effect is so small that we can't observe it unless we hold the material at a very low temperature, perhaps less than 1 degree above the absolute zero. Now at that kind of temperature, we can detect changes which are as small as a millionth of a degree or less. Now, the other problem we've got is that having learned how to do that, we're faced with the fact that the dark matter events are very rare. We expect, in fact, only about one a day in perhaps a kilogram of material like this. Now, that makes life very difficult because at the surface of the Earth, that one a day would be swamped by the other types of radiation which we have around us. Well, the problem is that we've gone 1,000 meters deep and got rid of all the cosmic rays from the surface. But we're still left with very small amounts of radioactivity in the rock which forms the walls of the cavern. Now, these levels of radioactivity are, in fact, very low by any normal standards, but they're still too high for us. And the reason for that is that it can cause events in our target which are at a greater rate than the dark matter events which we are searching for. So we have to solve this problem in the following way. We install in the cavern a large water tank and fill this with very pure water, which is non-radioactive. And this water will have the effect of absorbing almost all of the radioactivity from the walls of the cavern. So if we suspend our experiments in the middle of this water tank, then we will have the ideal environment for searching for the very rare dark matter events which we're searching for.
What we know about dark matter is that there's a lot of it. if it was, for example, in the form of old exam papers, this is actually a question I was asked in my final undergraduate exam, what would be the observational consequences if all the missing matter in the universe was in the form of old exam papers? It turns out this can't be the case, because you wouldn't be able to see far away galaxies, because the exam papers would fill space so well it would be opaque and you couldn't see far enough. So it probably has to be pretty transparent, otherwise it would just block our light. So we need very large amounts of the stuff out there. So we need something that's transparent, that weighs an awful lot and doesn't shine. Okay, now we absolutely have exhausted all human knowledge of the stuff. There's one other thing we can now work out about it. If it was made of normal matter like protons and neutrons, then just after the Big Bang it would have been involved in nuclear reactions and would have made some different elements appear on Earth. So the fact that we don't see these weirdo elements tells us that most of the dark matter can't be made of normal neutrons and protons. So it must be made of something else. So we know an awful lot about what dark matter is not. It doesn't shine. It's not made of normal protons and neutrons and things like this. It's very heavy, and it's transparent. And that is, I think, the sum total of human knowledge of what dark matter is. Questions or comments about that?
So when there's an anomaly between observation and theory, I think there's two possibilities. One is that you haven't observed everything, or there's something else out there, which is the dark matter theory. Is there any possibility that we just haven't quite got gravity sorted out yet? We know there's a problem with gravity in quantum mechanics. Is there any chance that we just haven't tested it properly, or that it's not quite complete yet? Einstein hasn't finished.
Okay, well the question was, could it be that instead of there being this huge amount of invisible, undetectable stuff, this is the sort of thing theorists love. You invent a particle that no one can see, can never detect, just floats around and does exactly what you want. That's, the theorists love this. They can publish hundreds of papers about it, no one can ever prove them wrong. But it could be that maybe we just don't understand gravity well enough. Because the whole reason we think it's there is because these things on the outskirts of galaxies are moving too fast. And the way we know they're going too fast is we use our law of gravity to work out how fast they should be moving. So if our law of gravity is wrong, then maybe we don't need any of the stuff. And this is indeed a moderately respectable theory. It's called modified Newtonian dynamics, or MOND. And this theory says that in fact, gravity does not quite obey the law we think it obeys. It obeys a slightly different law. We know that our normal law of gravity, which is Newton's equations of gravity, work extremely well on the scales of our solar system. Because we send spacecraft all over the place, they generally arrive where we want them to, unless someone failed to convert the units from imperial to metric. And who would do that? NASA, of course, did this. But by and large, assuming no one stuffs up their unit conversions, spacecraft go where we tell them to. But it could be that there's some new law of physics that only occurs on really, really big scales. For example, Newton's laws of motion were invented by Isaac Newton 400 years ago, 200 years ago, and they work very well for things like the mass of an apple, or me on a bicycle, or something like this, which is why they lasted for several hundred years, because for things that weigh a few kilograms, travelling at a few meters per second, they work perfectly accurately. It's only when we started getting down to things going either very close to the speed of light, or very, very small, they started breaking down. We needed new laws, in this case quantum mechanics and relativity. And so it could be that there's a third great theory of physics waiting to come that only kicks in at very big scales. That on scales of 100 billion metres or 1,000 billion metres, which are the biggest things we've ever done tests on with spacecraft, our laws of physics seem to work pretty well. But maybe when we go to much bigger scales, we need some new laws of physics, just as we had when we went to very small scales, and that could explain all this. And some people believe this, and some people don't. So once again, we don't know about it. There is another possible clue that something weird is going on, which is that the furthest out spacecraft the humans have ever sent, Pioneer, has been showing some anomalous behaviour. It's been decelerating back towards the solar system faster than predicted by the laws of gravity. Pioneer was a very simple spacecraft. It was basically a spinning oil drum with antennae stuck on the outside. And so it shouldn't really do very much. It didn't have any rockets on board to leak. It should just basically fly. And it was flying at not quite the right rate. And so that might be another sign that something funny is going on here, or it could be that someone stuffed up in the telemetry somewhere. So there could be something weird going on here, or maybe there isn't. So, to conclude, there's actually quite a lot left to discover in astronomy. We haven't actually quite finished the field yet. There are some pretty big questions we do not know the answers to. And in fact, there are probably some pretty big questions we will never know the answer to. In fact, the one thing that really worries me is that astrophysics is actually still very common sense compared to physics. Anyone here who's ever studied quantum mechanics will know that it is seriously weird stuff. I mean, really seriously weird. Most bits of physics you study it, and eventually, it makes sense. Quantum mechanics, that never happens. You get used to it after a while. Oh, yes, of course things can be in the same place at different times, and yeah, that's fine. You get used to it, but it never makes sense. And this also applies to people who invented it. It never made sense to them. They got used to it, they can use it. Every computer in the world uses quantum mechanics. We're very good at using it, but it doesn't make sense. It's very weird. It's very much against the way our brains work. Whereas most things in astrophysics seem to make sense. Objects move around, they behave in normal ways. It all seems very common sense, just like behaviour on Earth on a bigger scale. And that worries me a bit. It worries me because we actually know sod all about anything in space. We're just stuck here on this little dot called the Earth, staring away at the huge distance. And it could well be that these things up there are very, very much weirder than we think. And the only reason we think we understand them is because of our ignorance. If we actually get up close to them and measure them the same way that we can measure what's happening in some quantum mechanical system, we'd start discovering that everything we see in space is a whole lot weirder than we think it is. Thank you very much.